Diophantine equations are those that are to be solved in the integers. The most common type of Diophantine equation is the linear equation in two unknowns, ax plus by equals c, where a, b, and c are integers, and a and b are not simultaneously zero. The name Diophantine honors the ancient mathematician Diophantus, whose work in the field was of great relevance. Diophantus influenced later algebraic notation as well as the study of many number theorists. Little is known about his life. Indeed, one of the few things we do know about him is how much he lived. This information comes from a famous epigram problem which states, "His boyhood lasted a sixth of his life, his beard grew after 1/12 more, and after 117 more he married, and his son was born 5 years later. The son lived to half his father's age, and the father died 4 years later after his son." And that, well, guess what, translates into a nice Diophantine equation, of the form, with solution 84, so yeah, our boy must have lived about 84 years or so. Diophantine equations can have any number of unknowns, although, as said before, the most common type of such equations is the linear equation ax plus by equals c. A solution to it is a pair of numbers x0 and y0 such that a times x0 plus b times y0 equals c. A linear equation of this kind can have many solutions. For instance, 3x plus 6y equals 18 has the following as valid possible solutions. On the other hand, in some cases there will be no solutions at all, as with 2x plus 10y equals 17. Well, that makes sense analytically. After all, the left-hand side of the equality will always be even regardless of a choice for x and y, while the right-hand side will always be odd. So, you might be wondering, then how do I know, generally, if a solution exists? And if it is that the case, how can I write all solutions systematically? There are two theorems that will help us a lot in answering these questions. Well, our first theorem. For a linear Diophantine equation ax plus by equals c to be solvable, it is necessary that the greatest common divisor between a and b divides c. The proof is very straightforward. Let d be the GCD between a and b. We know that there are integers r and s such that a equals dr and b equals ds. Therefore, if a solution x0 and y0 exists, we may write, from which we arrive at the conclusion that d must divide c. Alright, that's cool and all, but let's now pause and try solving an actual problem. For instance, take the equation 172x plus 20y equals 1000. Where do I even start? Right, if we are looking for solutions, we must first check if there are any. We can do so by applying theorem 1. We use the Euclidean algorithm to find the GCD between 172 and 20. If you don't know what the Euclidean algorithm is or how it works, you might want to take a look at this first and then come back. So the GCD between 172 and 20 is 4, and 4 divides 1000, so we know a solution must exist. Now it's useful to notice that solving a linear Diophantine equation is pretty much finding a linear combination of some sort. You don't see that? Bear with me. We're first going to find 4 as a linear combination of 172 and 20. We do that by working backwards our previous equations for the GCD. We solve each of them for the remainder. Now we substitute the expression for 8 in the expression for 4. Now the one for 12, and the new one for 4. There you go. If we multiply both sides now by 250, that is 1000 divided by 4, we get. Nice. Our solution then is the pair 500 and minus 4250. It's important to notice that these manipulations were done conveniently, so that we are left with an expression for 4 in terms of 172 and 20. We did not evaluate any operation with 172 and 20. Rather, we just tried to simplify those values that we did not want in the end. Alright, but notice this is not the only solution. With effect, the pair 5 and 7 is also a solution. The only positive solution, in fact. To find all solutions for these equations, we make use of the following theorem. Let x0 and y0 be any solution, then all other solutions are given by, where t is an arbitrary integer. I will skip the proof of this for now, but if you want me to make a video covering the topic, let me know in the comments. Anyway, what this means is that to find all solutions to a linear Diophantine equation, we only need one solution, and then we can write the rest of them in terms of this one particular solution. Back to the example 1, we found a solution, namely 500 and minus 4250. Hence, we know any other solution can be expressed as x equals 500 plus 20 over 4 times t, and y equals minus 4250 minus 172 over 4 times t for some integer t. Cool! An interesting remark is the form the theorem takes when a and b are relatively prime, that is, when the GCD between them is 1. In this case, all solutions are given by x equals x0 plus bt and y equals y0 minus at for integral values of t. Diophantine equations tend to emerge from situational problems or word problems, like the one about the life of Diophantus we talked about before, or the famous Chinese problem of 100 falls. If a cock is worth 5 coins, a hen 3 coins, and 3 chicks together 1 coin, how many cocks, hens, and chicks, totaling 100, can be bought for 100 coins? This leads into the following system of equations. There are many other clear examples of Diophantine equations, most of them non-linear, but more interesting. Last one is from Ross's last theorem, which for sure you might have heard about. There also is the equation w cubed plus x cubed equals y cubed plus z cubed. One of the solutions is the following. Curiously, 1729 is the well-known Ramanujan's taxicab number. Thanks for watching until here. Hope you enjoyed the video. Although I didn't go much in depth into the topics we were covered, I hope to have helped at any level. If you want to support my content, follow me on Instagram, leave a like, a comment. Anyway, see you!